Hi, it's Ryan. This is a video on our first Kirchhoff's rules example. This circuit should actually look a little familiar. It should feel a lot like the last example that we had on combination circuits, only this time we're going to solve it using Kirchhoff's rules instead of our circuit laws that we gave you before. So I've written out the problem to save us a little time. It says, using Kirchhoff's rules, calculate the current through, the voltage across, and the power dissipated by the resistors in the following circuit. So you'll be given a problem like this, probably on your midterm exam or celebration. Anyway, this is a little simpler than a Kirchhoff's rules problem generally is because there's only one power supply. I just wanted to take this simple example and apply Kirchhoff's rules one step at a time, and then we'll do a more challenging example next. So if we recall from our notes on Kirchhoff's rules, the first thing we have to do is arbitrarily label our currents. So I'm going to go ahead and just at random draw in some currents in here. And so like normal, I'm just going to have my total current leaving the power supply. And if I have a total current leaving the power supply, then that means I need to have it return to the power supply. I total will hit this first junction. We can label it junction 1. And then we could then label junction 2 as well. When I total is incident or it goes into junction 1, it will cease to exist and two new currents will come out. We'll have I2 and I1. I2 will be forced through R3 and then back into junction 2, and I1 and I2 will combine to give us I total. So the first step of Kirchhoff's rules is to simply input these currents in any direction we see fit. I didn't really pick a direction as much as just go ahead and stick to how we've been doing this. So that first bullet in our Kirchhoff's rules conventions is taken care of. The next one would be to arbitrarily label our loops. And so when we talk about a loop, in general, what we're talking about are any part of the circuit that we can create a closed loop. For example, this is one loop. We could label this particular loop, loop A. So I'm going to take a counterclockwise circle like so and label this loop A. And I'm going to show that we're going to start loop A at that point. Now take a second and decide, are there any other possible loops? Well, if we look at this part of our circuit, it forms a closed loop. And so we could label this loop, loop B. So I'm going to go ahead and label this loop B. And we're going to say, let's start loop B at that corner there. Finally, we could choose one more loop. If you look around the outside of the circuit, this forms a different closed loop. And so that we could label as loop C. I think I actually made my circles going clockwise, and I never do that. So it's okay. I'm just going to keep with my clockwise circles this time. I normally do counterclockwise. And so this represents this outside loop, ignoring this branch. So we've arbitrarily chosen 3 different loops. Maybe we could also note that we'll start loop C at this corner. And now we have to go through and apply the final set of conventions, and that's really the point of these loops. So we're going to now apply the junction and the loop rules. So let's look at the junction rule first. It's very straightforward. Keeping in mind the junction rule is that the current into a junction must equal the current out of a junction. And it looks like we have two junctions here, and I would imagine that both junctions will end up yielding the same equation. So we're going to just go ahead and look at junction 1 for our junction rule. The current in must equal the current out, and so if we look at our junction, we have I total going into the junction, and we have I1 and I2 leaving the junction, or going out of the junction. So in, we have I total, and out, we have I1 plus I2. And if you were to look at junction 2, wouldn't we end up getting the same thing? We would have I1 plus I2 going into it, and I total leaving. So we're going to go ahead and just box this in. This is our first equation in case we need it. But obviously there are too many unknowns to solve this. We need to go ahead and apply our loop rules. So this was our junction rule. Our loop rules, we have 3 loops to look at. We have A, B, and C. And technically, according to one of our conventions that I gave you in the previous video, we really only need 2 of these 3 loops because we need one more loop rule than junction rule to solve this. But just because this is practice, I'm going to go ahead and determine all 3 equations for these loop rules, keeping in mind that the loop rule is that the sum of the voltages around loop A must be 0, the sum of the voltages around loop B must be 0, and the sum of the voltages around loop C must be 0. So looking at the picture, we're going to slowly go in the clockwise direction because that's what I arbitrarily chose, starting from this point, and we're just going to go around loop A until we run into any component like a resistance or a battery. And then we'll apply those conventions that we listed in the last video. So here we go. We're going to get the equation for loop A first, and we're going to do that by starting at this corner because I randomly chose that, and we're just going to kind of go around the loop. We're forced to go down at junction 1 because loop A is this first loop here, and we get to resistor 1. Now notice if we're going clockwise around the loop, we're going to actually go in the same direction through R1 that we randomly drew the current going through R1. And so looking at our conventions from the previous video, we see that if we follow the current through a resistor, then the voltage drop is negative. So I'm going to show this in little steps. So we're following the current. We're going in the same direction as I1 through R1 and then through R2. So both of these will be negative. So I'm going to show this in steps even though you don't have to do this necessarily. So we know that we'll have negative V through R1 plus a negative V through R2, and we're getting those negatives because we're following I1 through R's. And then we'll get to junction 2, and we'll have to continue on loop A until we get to the battery. And in the battery, we're going from low, the negative terminal, to high. And in our rules, we know if we go from low to high, we'll be getting a positive potential difference. So this would be plus V for the battery, or V total. And we know that the sum must be equal to 0. Well, using Ohm's law, we actually, and this is where most people will just write their equation, we know that V for R1 is just I1 R1 minus I1 R2, because I1 goes through R1 and R2. and then we have to add the V total, which was the 12 volts. And so the last thing we can do, and we might note, this is one of the only places in our class that you can get away without writing your units on every number. So I'm going to rewrite this equation with just some of the known values. We've got negative R1 is 200 ohms, so we're going to say 200 I1 minus R2 was 142 ohms, so we'll say 142 I1 plus, and V total was 12 volts. And so this is our first equation that we can get using the loop rule for loop A. As you can see, this equation has one unknown, and so this is a very useful equation. It looks like we can get I1 from this equation, but before working through this, I just want to keep going with our loop rules. We're going to get the equation for loop B next, and so we're going to look at loop B, which we said we're going to start in this corner, and we're going to go clockwise around loop B, which is like this. And so we need to start here and go to junction 2. We haven't gone through anything yet, so we don't add anything to our equation. But then we have to go up through R2 and R1, and it looks like if we go up through R2 and R1, we're going against the direction that we drew I1 in. If we go through resistors against the current, then we add positive voltages. We're going against I. And so for our first two numbers in our loop rule, we can go ahead and do positive I1 R2 plus I1 R1. So we have plus V through R2 plus V through R1. We went this way. Then we're going to end up going to the right. There's no components. And then we're following I2 through R3. And if we go with the current through a resistor, we know it's going to be a negative potential difference. And so we would have minus the V through R3 equals 0. But we know that V is just IR, so I can go ahead and put, so for the voltage drop across R2, we would have R2I1 plus R1I1 minus, and then for the voltage drop across R3, we have I2R3. R3I2 equals 0. And so I can go ahead and write in the numbers again. So we'll have R2, that was the 142 I1, plus 200 I1 minus 61 I2. And it looks like from this we can get an expression for I2 with respect to I1. And if we use I1 from this equation, we could then get I2 from this equation. But just for the sake of practice, we're going to do a third loop, loop C. And loop C was described as this outer loop, where we're going to go clockwise around only the outer loop, starting from this corner. So starting from this corner, if we go up through the potential difference, we'll be going from low to high again. If we had been going this way through the battery, it would be from high to low, but we're going clockwise like our arrow shows. So we're going to be going from low to high. So we have the 12, and it's positive for the voltage for that. And then we're going to turn right because we have to, and loop C is the outer loop, so we're ignoring junction 1 and junction 2, and following I2 through R3. That means we have a negative I2 R3, so we'll have minus, and R3 was the 61 times I2, And then we can continue on until we're back to C. We didn't go through any more components. So this is equal, so this is equal to 0. And it looks like from this one we can actually solve for I2. So it turns out if I was doing this, I would probably choose to use loop A and loop C. And maybe it would be beneficial to create a solutions table for this. And so we have our resistor, our current, our voltage, and our power dissipated by. So it looks like I would use loop A to get I1. So we'll say using loop A, we know that we'll have 200 and 142. We have to put those together, so we'll get 342, and it's negative. So we'll have negative 342 I1 plus 12 equals 0. And notice I'm just rewriting this equation, and I combined these two because they have the same variable. And so I can solve for I1. I1 is, and so I would add this over and divide 342 by both sides. And so I1 will be 0.035 amp. Knowing I1, we can get, or knowing that I1 goes through R1 and R2, we can input the current into our solutions table. And we can also calculate the voltage across each component. And it looks like these are working out to the total 12 volts. We know that looking at our picture, I1 needs to drop a total of 12 volts across R1 and R2 together. They're in series, so their voltage drop should sum to the total voltage. And it looks like they do, minus a little bit of rounding. And that also means we could calculate the power dissipated by each. And it looks like then we could use loop C to get I2. So we could say using loop C, we can get I2 is equal to, and it looks like it'll just be 12 over 61 amps. And so that will end up being 0.197 amps, so almost 0.2. And that means we'll, of course, get the 12 volts to be dropped across R3, and we have the 2.36 watts. If we add these all together, we would get the total power dissipation of approximately 2.8 watts. And so we've answered the question. The other thing that we could do is we could use the junction rule to get I total, to get power dissipated by the circuit if we wanted, but this should do it.